All right, get ready, because today we're going deep, really deep, into the world of EEGs.
Brain waves.
Yeah, those brainwave tests.
You always see them in like the movies and stuff.
Exactly.
Those squiggly lines.
But you don't need to be a doctor or a brain surgeon to follow along today.
No.
We're going to break it all down.
Make it nice and easy.
And actually, EEGs, I think, are one of the coolest tests out there.
Oh, absolutely fascinating.
Because it gives us this direct look
This window.
into what's happening.
Yeah, into the electrical activity in our brains.
So an EEG, an electroencephalogram,
Yeah.
it measures the electrical signals in our brain.
Right, the tiny electrical currents that are generated by all of our brain cells.
Okay, so how does that actually work?
So they use these electrodes, they place them on the scalp, and they can detect these tiny currents.
Okay, so it's painless.
Completely painless, non-invasive.
They're not like going into your brain or anything.
No, nothing like that.
That's good.
Just
Yeah.
on the surface.
But how do they make sure that everyone's EEG is like
Standardized, yeah.
comparable?
That's a great question because everyone's head is different.
Yeah, exactly.
Sizes and shapes. So they use what's called the 1020 system.
The 1020 system.
It's a standardized placement for these electrodes. So it's kind of like a map of the head.
Like a GPS for your brain?
Exactly. They use anatomical landmarks, like the nation.
What?
The nation, that little dip at the top of your nose.
Oh.
And then the inion, the bump at the back of your head.
Yeah, okay.
To kind of get a consistent
All right, so they're measuring.
measurement.
And then they're putting the electrodes
Yeah.
on specific points based on...
The size of your head. Yep.
Wow, so they really thought this through.
Oh, yeah. It's very standardized.
And this helps us to find then like the alpha waves and all the other different brain rhythms.
Precisely. And it allows us to compare EEGs across different people.
Okay.
And different studies.
In different studies, that makes sense.
So we're all on the same page.
So alpha waves, those are the ones that everyone always talks about.
The famous ones, right?
Those are the relaxing ones.
Yes. They're associated with a relaxed, wakeful state.
Okay.
And you'll see them most prominently at the back of the head, the occipital region.
Okay, now here's something I always found really interesting.
Okay.
The alpha waves can be different on each side of your head.
Yes, that's right. The amplitude can be asymmetric.
And if it's a really significant difference, like more than 1 hertz,
Right?
it could be an indication that there's slower activity
That's mixing in.
Yeah.
Which could be a sign of an underlying issue.
So the side with the lower frequency is the problem.
Yeah, that's the one.
That's so counterintuitive.
I know, right?
I always thought it was a higher frequency.
You would think, right. But it's kind of like the slower activity is like a disruption
Oh.
to that normal, faster alpha rhythm,
Okay. So it's like an off-key instrument.
Yeah. In an orchestra.
Yeah. Okay.
Throwing off the harmony.
That makes sense.
Yeah.
All right. So we've got alpha for relaxing, but what about when we're moving?
Yes. Then we have what's called the MU rhythm, which is found over the central region of the brain, so kind of like a headband.
So if I'm like imagining myself winning Wimbledon, my MU rhythm's just like...
Firing away.
Yeah.
That's so cool.
It's amazing how closely it's tied to motor activity.
So there are actual patterns that we look for.
Absolutely.
It's not just a bunch of random squiggles.
Not at all. It's like a language.
And you can tell by the shape.
Yeah, the MU rhythm often has this really distinctive arc-like shape.
Oh, wow.
On the EEG.
So this is getting way more interesting than I thought it would be.
Oh, it gets even better. The MU rhythm actually decreases in amplitude.
Okay.
What we call attenuation when you move.
Oh, really?
Or even just think about moving.
Well, so it's like the brain is saying, okay, enough planning, now we're going to do this, and then it quiets down. Quiets down that MU rhythm.
Wow, that's wild.
Isn't that fascinating?
Yeah, that's amazing.
And this actually helps us distinguish it from other rhythms that might look similar, like the Saganic rhythm.
Saganic?
Yeah, which can look similar, but it doesn't attenuate with movement.
So it doesn't quiet down?
No.
Wow, so you really have to keep these little subtle things in mind.
Absolutely. The details matter.
When you're reading these EEGs.
Yeah, the subtle differences.
All right, what about when we're sleeping?
Sleep. We see a variety of different rhythms during sleep.
So there's sleep rhythms too.
Oh, yeah.
Ah, this is great. One of the most prominent ones is what's called the delta rhythm.
Delta?
And those are these slow, rolling waves that typically show up during deep sleep.
So delta waves are like the brain's just like powering down.
You could say that, yeah. It's like in, deep sleep mode.
Okay.
But here's the thing.
Okay.
If you see delta waves when someone is awake, that could be a red flag.
Oh, really? It might suggest there's an issue in that specific area of the brain.
So they're supposed to be sleeping, if they're awake and they're having these delta waves,
Right, that's when we start to worry.
then that's a sign that something's not quite right.
Yeah, not quite right. Something to investigate further.
Okay. It's good to know.
Yeah, so it's not just the rhythms themselves, but also the context, right?
So, like focal delta activity,
Exactly.
that would be delta waves just in one specific area of the brain.
Right, concentrated in one area.
And that could be a sign
of something called localized brain disease.
It's fascinating how we can tell so much
Yeah, just from these brainwave patterns, right?
by these little squiggles.
Amazing.
It's incredible.
And did you know that delta waves were first discovered by a young physiologist
No
who
way.
brought his, back then, this huge, bulky EEG machine into an operating room?
What?
Yeah, to study patients under anesthesia.
Oh my gosh, that's dedication.
Talk about dedication, right?
Cool.
And that's how we discovered these slow waves.
So even back then, they knew that there was something to this.
Oh, absolutely. They were pioneers.
Now we've got delta waves. Are there other sleep rhythms too?
Oh, yeah, there's a whole bunch of them.
Like what?
Like sleep spindles,
Okay.
vertex sharp waves,
I've heard of those.
and then those sawtooth waves during REM sleep.
Oh yeah, REM sleep,
Yeah.
the dreaming.
Exactly. All playing these unique roles in our sleep cycle.
So it's not just delta, it's all these different things.
It's a whole symphony of activity happening during sleep.
A symphony, I like that.
Yeah.
Okay, so we've got these sleep rhythms, we've got alpha, we've got mu. Are there
What else?
other things that we see on EEGs?
Well, we've talked about the normal rhythms, right?
Right.
But sometimes we see things that might look a little alarming at first,
Okay.
but they're actually harmless.
Okay, like what?
For example, there's something called benign epileptiform transients of sleep.
Benign.
Yeah, they're also known as small, sharp spikes.
So bets are the same thing as small sharp spikes.
Exactly.
Oh, wow.
Which is kind of funny because the name sounds scary,
It does sound scary.
but they're actually totally benign.
So they're harmless.
Harmless, yeah.
Okay, so why do they call them epileptiform if they're benign?
Because they can kind of look like seizures on the EEG.
Oh, but they're not.
They're not seizures.
No, not at all.
So these bets, these small, sharp spikes,
Yeah.
where do we usually see those?
You see them primarily during drowsiness and light sleep,
Okay,
and they're especially prominent in the temporal regions of the brain.
the temporal region.
It's kind of like above your ears.
Above your ears. Okay, all right. So they're harmless.
Totally harmless.
But it's important to know about them
Absolutely.
so that we don't freak out
Exactly.
when we see them.
Yeah, because they can be mistaken for abnormalities.
So someone who doesn't know what they're looking at
Right.
might think that there's a problem when there's really not.
Exactly.
Yeah.
That's why education is so important. I like that. So we're getting educated today.
That's right.
Okay. What else do we need to know about reading EEGs?
So we've talked about normal rhythms, benign findings,
Right.
but then there's this whole other world of what we call artifacts,
Artifacts. Okay.
which are basically non-brain signals that can contaminate the EEG.
Contaminate.
Yeah, it's like noise.
Okay. Good.
It's mixed in.
So it's like trying to listen to a podcast
Yes,
when there's a lot of background noise.
exactly.
Oh.
And it can make it really tricky to interpret the EEG.
So what are some examples of artifacts?
Oh, common culprits are things like eye movements.
Eye movements can cause artifacts.
Yeah, they create these electrical signals,
Yeah.
muscle activity, which we call EMG artifact.
It's GMG. Okay. Now, I remember reading that like lateral eye movements.
Yes.
Like if you're looking side to side,
Right.
that can create those artifacts.
Exactly. They create these really distinctive artifacts with opposite polarities in the left and right frontal regions.
So it looks like there's brain activity,
Yeah.
but it's really just your eyes.
It's just your eyes moving, yeah.
Wow, that's wild.
And then that ECG artifact, that can actually look a lot like some brainwave abnormalities.
Really?
Yeah, it can be tricky.
So how do you tell the difference?
Well, that's where the expertise of the EEG interpreter comes in, right?
Yeah.
They're trained to recognize these subtle features.
Okay, so you really have to know what you're doing.
Absolutely. It's like being a detective.
Okay.
You're looking for clues.
I like that analogy.
Yeah. And you have to piece together the puzzle of what's happening in the brain.
The brain puzzle.
And sometimes those puzzle pieces aren't even from the brain itself.
That's true, because we've got the artifacts that are,
Right. Throwing us off.
so we've got all these different things that could be going on.
It's complex.
It is complex, yeah.
But that's what makes it so fascinating, right?
I know, and we're just getting started.
It's just scratching the surface.
I'm excited.
You. Welcome back. You ready to get into some of these abnormal patterns that can show up on an EEG?
Yeah, I'm ready to dive into that world.
All right, let's do it.
I'm particularly curious about those periodic epileptiform discharges?
So there are these recurring
Okay.
sharp waves or spikes
Okay.
that often indicate some sort of acute brain dysfunction.
So if you're looking at an EEG and you see these PLEDs, it's a pretty big red flag.
Yeah, major red flag that something needs attention.
Okay.
It could be from a variety of causes like strokes, infections, metabolic disturbances, even seizures themselves.
Okay.
So yeah, if you see PLEDs, time to dig deeper.
Wow.
Figure out what's going on.
And then there's these even scarier sounding bilateral periodic epileptiform discharges.
BiPEDs.
BiPEDs, yeah. What makes those worse than PLEDs?
So both P can occur on both sides of the brain, but BiPEDs are synchronous.
Synchronous.
Meaning they happen at the same time on both sides.
Okay.
And they also have this distinctive large bifrontal field.
Bifrontal, so at the front.
Yeah, at the front of the head.
So it's like synchronized PLEDs.
Yeah, you could think of it that way.
And why are those worse?
Well, they often reflect a more widespread disturbance in brain function.
So a bigger part of the brain is kind of out of whack.
Yeah, like a larger portion of the orchestra is playing out of tune.
Oh, I like that analogy.
Yeah.
Going back to that.
Back to the music.
Okay, that makes sense.
Yeah.
Now, what about generalized periodic discharges? GPDs. Those sound ominous.
They are.
What are we talking about with those?
So those often signal a global disruption in brain function.
Global.
Yeah, meaning the whole brain is affected.
Oh.
They can manifest in various forms, but one characteristic type has this triphasic waveform.
Triphasic.
Yeah, meaning each wave has 3 peaks.
So you can see that pretty easily on an EEG.
Yeah, it's quite distinctive.
Okay.
And these triphasic GPDs are frequently seen in metabolic disorders.
Like what?
Particularly hepatic encephalopathy.
Hepatic encephalopathy. That sounds like a liver problem.
It is.
What does the liver have to do with the brain?
Well, it's fascinating, right?
Yeah.
So hepatic encephalopathy occurs when the liver is damaged.
Okay.
And it can no longer filter toxins from the blood.
Okay.
And those toxins can then affect brain function.
So even though the root cause is in the liver,
yeah,
the brain is affected.
And we can see it on the EEG.
That's wild. It just shows you how interconnected everything is.
It really does.
It's incredible.
Yeah.
All right. Are there any other abnormalities that we should be aware of?
Well, remember how we talked about delta waves being associated with deep sleep? Well, there's a pattern called burst suppression.
Burst suppression.
It's characterized by these periods of suppressed brain activity.
Okay.
Almost like a flat line on the EEG.
Oh, wow.
Alternating with these bursts of electrical activity.
So it's like the brain is switching on and off.
Yeah, pretty dramatic, right?
Yeah.
And while this pattern can be intentionally induced during deep anesthesia,
okay,
seeing it spontaneously is a major red flag.
So if someone's not under anesthesia and you see that?
Yeah, not a good sign.
That's bad.
It often indicates severe brain injury or dysfunction.
So what kind of conditions would cause that?
You might see it in things like hypoxic ischemic encephalopathy.
Okay.
Where the brain's been deprived of oxygen.
Okay.
Or in certain types of epilepsy.
So it's a sign that the brain's really in trouble.
Yeah, profound disturbance in brain activity.
All right. This is all starting to make a lot more sense now.
Good.
I'm starting to see how EEGs can really help us to understand what's going on in the brain, both in normal and abnormal situations.
Exactly. It's like a window into this incredibly complex organ.
And it's not just about the squiggles. It's about the context, too.
Absolutely. It's all about the context.
You really have to know what you're looking for.
The whole picture.
Okay, now we talked about those benign findings earlier, like bets and small, sharp spikes.
Right.
Is there anything else that we should be aware of?
Yeah, there's another one called phantom spike and wave discharges.
Phantom spike and wave. That sounds kind of spooky.
I know, right? The name's a little ominous.
But they're benign.
They are benign, yeah.
Okay.
They appear as these synchronous bursts of activity, typically occurring at a frequency of 5-6 hertz.
Synchronous, so like happening on both sides of the brain. Phantom spike and wave is harmless.
Totally harmless, yeah.
Okay.
What's interesting about them is that the spikes themselves can actually be less prominent than the following slow waves in this pattern.
So it's like the slow wave is the echo of the phantom spike.
Exactly. It's like a phantom echo.
I like that.
Yeah.
So if they're benign, why is it important to even know about them?
Because it's important to differentiate them from true epileptiform activity.
Okay.
Right? So that we're not misinterpreting them.
Okay, that makes sense.
And you know what? It all comes down to analyzing the waveform carefully.
Okay.
Understanding its distribution across the scalp.
So even the benign patterns can be tricky.
They can be.
if you don't know what you're looking at.
Right. That's why the expertise of the EEG interpreter is so important.
They're like brain detectives.
Yeah, brainwave detectives.
I like that.
Yeah.
Okay, so we've got those.
What else? What else do we have?
What about salt bridges? You mentioned those earlier.
Oh, the salt bridges. Yeah.
Yeah, those unwanted electrical pathways between electrodes that are caused by things like sweat or conductive gel.
So it's like a short circuit?
Yeah, kind of like a short circuit.
And that can create artifacts. Oh, it can create some really bizarre artifacts that might be mistaken for brainwave abnormalities.
I bet that leads to some head scratching for the interpreter.
Definitely.
So what does a salt bridge actually look like on an EEG?
Well, imagine you're looking at a busy freeway on the EG,
Okay.
lots of activity.
Okay, yeah.
And then suddenly there's a section where the traffic just disappears.
Oh, wow.
That sudden drop in amplitude in one or more channels could be a salt bridge.
So how do you know if it's a salt bridge or something else?
Well, that's where you look at the other channels, consider the electrode placement,
Okay.
and use your detective skills to figure it out.
Put those clues together.
Right, and experienced EEG technicians are usually very good at spotting and correcting these issues during the recording itself.
So they're watching out for it.
Oh yeah, they're on it.
But sometimes they can be tricky to catch.
They can be sneaky.
So it's a good reminder that even with all this amazing technology, the human expert is still really important.
Absolutely essential.
Right, so we've talked about salt bridges. We've talked about all these different patterns.
We're getting there.
Is there anything else?
Well, there's one more abnormal pattern I'd like to discuss.
Okay, bring it on.
This one is called hypersynchronous slowing.
Hypersynchronous slowing.
Hypersynchronous slowing.
Yeah, it refers to these highly regular slow waves that can be triggered by hyperventilation.
Wait, hyperventilation like when you breathe really fast?
Exactly, like when you're breathing really fast and deep.
And how does that affect the brainwaves?
Well, it's a standard part of many EG procedures.
Okay.
And for most people, this type of slowing resolves quickly after stopping hyperventilation.
Okay.
But if it persists, it's considered abnormal.
So it's like the brain's having trouble shifting back to its normal rhythm
Yeah, good way to put it.
after being thrown off by the hyperventilation.
Exactly. And we call this persistent slowing the rebuild-up
Or
phenomena.
the rebuild-up phenomenon.
Ex-
Yeah.
Okay.
It can be a valuable clue in diagnosing certain conditions.
Wow, who knew breathing could tell us so much about the brain?
Right. It's amazing what we can learn from EEGs.
It's incredible.
Yeah.
We've covered a lot of ground today,
We have.
from normal rhythms to artifacts to some pretty intense abnormalities.
A whole spectrum of brain activity.
My brain needs a little break to process all this,
I hear you.
but I'm excited to dive into the next part of our deep dive.
All right, sounds good.
All right, welcome back to the final part of our EEG deep dive.
We're going to wrap things up here.
I feel like my brain needs a reboot after all of this.
A little bit of a brainwave break.
Exactly.
So we've talked about all kinds of patterns, normal, abnormal artifacts.
It's been a lot.
It has.
But is there a pattern that means there is no brain activity?
Yes, there is. It's called electrocerebral inactivity,
Electrocerebral inactivity.
or ECI for short.
Okay, ECI,
Sometimes also referred to as a flat EG.
a flat EEG. So that means like no brain waves at all.
Exactly. No detectable electrical activity, which, when confirmed using really strict criteria,
Okay.
is consistent with brain death.
So that's like the ultimate silence of the symphony.
Yeah, very profound.
Wow, it really makes you think about how important those electrical signals are.
Absolutely. For everything we do, think, feel.
Our whole existence.
Yeah, it's pretty amazing.
Well, I have to say, this deep dive has been incredible.
I'm glad you enjoyed it.
I feel like I've learned so much.
Hopefully, it's giving you a glimpse into the amazing world of EEGs and all the information we can get from them.
Yeah, those little squiggly lines are not so simple after all.
Not so simple, but so powerful.
And they can tell us so much.
About the brain.
Well, I want to thank you for guiding me through this EEG journey.
It's been my pleasure.
And for our listeners, we hope you found this deep dive informative and interesting. And we'll see you next time.
Until then, keep those brainwaves buzzing.